Can you see the shared screen?
Yes.
Okay, fine. So we in the Carbanion and their reactions, that was the first chapter in CH 343, that is fourth semester organic chemistry. In that, what we have spoken about Carbanion, what are the different factors required for the stability of Carbanion. Then some reactions where Carbanion is involved, that is aldol condensation, Claisen condensation, Perkin reaction, and Dickmann reaction. And then there are few synthetic applications of few molecules where carbanion is involved, and you can synthesize various synthetic compounds. In that, malonate ester, Wittig reagent, and acetoacetic ester, these three reagents are there whose synthetic applications we are supposed to understand in this particular chapter. So what is carbanion? So obviously we know that a carbanion is a carbon which carries negative charge. So carbanion is an anion of carbon. That is what we can say, that it is an anion of carbon. And okay, can you see the screen? Okay. So carbanion is nothing but carbon with negative charge. We had discussed about its geometry. So it is tetrahedral geometry with sp3 hybridization, and generally it is formed by removing a hydrogen or some group, like for example some X group from carbon, to get a negatively charged carbon, that is called carbanion. Now, it is generally observed that those compounds which contain electron withdrawing groups, they can easily form carbanions. For example, you have methyl cyanide, methyl nitromethane, or acetaldehyde, or acetone, or ester, or you have CF3H, trifluoromethane, or you can have trichloromethane. Now here what you'll find, that all these molecules what we are talking about, they have electron withdrawing group. For example, CHO or CO or COOR, CF3. These are electron withdrawing groups. So if I have some electron withdrawing group and I have a strong base, then hydrogen or some group like X can be removed to generate a carbanion. So when I compare, if X is equal to hydrogen, then carbanion is called as a conjugate base of that compound. Okay, so generally hydrogen is removed, and it is a your this thing conjugate base of your molecule. So so the carbanion is a conjugate base. And we know that since there is negative charge, we can say that there is an empty sp3 hybrid orbital. We know that there are 4 sp3 hybrid orbitals after hybridization. 3 sp3 hybrid orbitals are occupied by bonding pair, and now one of them is vacant because of removal of this X, and now this is occupied by a pair of electrons. So this pair of electron makes this carbon negatively charged, and we call that as a carbanion, which is tetrahedral, and the angle, bond angle everywhere is 109.5 degree, like your sp3 hybridized molecules. This also shows the angle as 109.5 degree. Now mostly strong bases like soda amide or potassium amide, NaNH2, KNH2, or sodium alkoxide, potassium alkoxide, these are the bases generally used to remove X or hydrogen from your molecule. And as I told you that uh, you get a carbon then which is a trivalent, but its geometry is tetrahedral because it has 4 sp3 hybrid orbitals, out of which one is occupied by a lone pair of electrons. Now when this carbanion can be formed? Only when your molecule is able to give a stable carbanion, then only it will be formed. Now, so what are the different factors which will stabilize this carbanion? So the first factor, as you know, that in organic chemistry, whenever we talk about reactivity or stability, we talk about generally 3 to 4 effects. In that, inductive and resonance are the most common effects which will stabilize any species, for example over here carbanion. Now inductive, as we know, that is of two types, minus I and plus I. So obviously they will have different effects. what you will find that any molecule which any carbanion which is stabilized by minus I effect will be highly stable, and if it contains plus I effect giving groups, then that carbanion will be less stable. So in general, what we'll say that electron withdrawing group which impart minus I effect will make the carbanion highly stable, whereas if you have electron donating group in the molecule, then due to plus I effect, that makes the carbanion highly unstable. So plus I effect is going to make the carbanion unstable, whereas minus I effect is going to make the carbanion stable. Here one presentation we have shown that if you have an electron withdrawing group, and let's say this is carbanion where you have a negative charge on this carbon. If you have electron withdrawing group, that is minus I effect, then this carbanion, the charge is delocalized. That means it is taken by some other group, and if it is delocalized, then we say that that carbanion is stable. Exactly opposite thing will happen if you have electron donating group. Now already your carbanion is electron rich, it has a negative charge, and electron donating group try to give electrons to this CH2 minus. That means there will be electronic repulsion, and that will make this carbanion highly unstable. So if I have primary, secondary, tertiary and quaternary carbanions, then what I will find that a carbanion which is a primary will be less primary will be more stable as compared to a tertiary carbanion. Why? Because simple, you will find that in tertiary carbanion you have 3 R groups. In secondary carbanion you have 2 R groups. In primary carbanion you have 1 R or no R if it is methyl. Now R group has a tendency to give electrons. It is a plus I effect. Uh, uh, it shows plus I effect, and because the tertiary carbanion has 3 R groups, due to high plus I effect, tertiary carbanion becomes highly unstable, whereas primary carbanion are more stable as compared to secondary or tertiary carbanion. It is exactly opposite to your carbocations. As you know, that carbocations, tertiary carbocation is highly stable because their electron donating group stabilize the plus charge on the carbon, whereas negatively charged carbanion is always destabilized by plus I effect, and therefore primary carbanion is highly stable as compared to secondary and tertiary carbanion. Then another factor comes, that is the resonance. Again, we know that resonance is also of two types, that is minus R and plus R. Exactly same thing happens like your inductive, that your plus R will destabilize the carbanion and the carbanion will be becoming unstable. But if you have minus R effect in the molecule, in the ion, then that ion will be highly stable. So minus R effect stabilizes the carbanion, whereas plus R effect destabilizes the carbanion. So again, if you have an electron withdrawing group in your benzene ring, then that becomes a minus R effect. The CH2 minus will give its electron to the ring, and because of that, it becomes stable. Which are the electron withdrawing groups? So just now I spoke that there are some groups which show minus I as well as minus R effect. For example, CN, nitro group, or ketone, or aldehyde, or ester. These are the groups. They are electron withdrawing groups. Whenever they are attached to aromatic ring, they impart minus R effect and make the carbanion highly stable. But exactly opposite thing will happen if you have alkyl group or alkoxy group or amine group attached to your benzene ring, because they are electron donating group. Nitrogen, oxygen have lone pair of electrons which can be donated to the ring, and then the ring becomes electron donating, and this that will make the carbanion highly unstable. So carbanion stability, that means, is also decided by your um, uh, minus R effect as well as plus R effect. So what you'll find that anytime whenever you have minus I or minus R effect, that will stabilize the carbanion, whereas plus I or plus R effect will make the Carbanion highly unstable. So this was the second factor which we consider whenever we talk about the stability of Carbanion. Then there is a third factor which will also decide the stability of Carbanion. That is percentage of S character. As we know that your carbon can go three types of hybridization, that is sp, sp2 and sp3, and we know that if the your hybridization changes, the percentage of S character also changes. We know that percentage of S character is maximum for alkynes. It is in between alkane and alkynes for alkenes, and alkanes has less percentage of S character. What is the percentage? So you'll find that alkenes have 25% of S character, alkenes have 33.33% of S character, whereas alkynes have 50% of S character. It is observed that if the S character in any carbon increases, it becomes more electronegative, and that means if the percentage of S character increases, the electronegativity of carbon increases, which will make the carbanion highly stable. That means a carbanion of alkyne will be always highly stable as compared to carbanion of alkene and alkane. For example, we have ethane, we have ethene, and we have acetylene. This is your alkane, this is your alkene, and this is your alkyne. The percentage of S character in ethane, that is in alkane, as I told you, which undergoes sp3 hybridization, is 25, whereas in ethene, which undergoes sp2 hybridization, is 33.33, alkynes 50%. So what you'll find that the molecule acidity goes on increasing when I go from sp3 to sp2 to sp type of carbon. Acidity increases means what? Its tendency to give H plus ion increases. Now you can see any molecule when gives H plus ion will be converted into anion, that is the conjugate base of that compound. So if ethane gives its H plus, it will form this carbanion, ethyl carbanion. If ethene gives hydrogen, this will form vinyl carbanion. And if acetylene gives, then this acetyl anion will be formed. Now what you will find that since this anion has highest percentage of S character, this anion is highly stable as compared to this or this. That means the stability of carbanion goes on increasing when I go from this sp3 to sp2 to sp type of carbanion, and therefore sp carbanion becomes highly stable, or we say that acetylene is highly acidic in nature, or in general, alkynes form stable carbanion after losing their proton, hence they are acidic in nature. So many times this question is asked that why acetylene is acidic in nature, or explain the acidic character of acetylene. So you will say that acetylene is sp hybridized molecule which contains percentage of H character as maximum, that is 50%, and after losing H plus ion, the carbanion formed of acetylene is highly stable, and therefore it loses its proton very easily, or in other words we say that acetylene is a acidic molecule. As compared to ethene or ethane, acetylene or ethyne is a highly acidic molecule because of the high percentage of S character. So this is how you will explain the acidic character of your this thing, alkanes, alkenes, or alkynes. So this is the third factor which decides the stability of carbanion, and that is percentage of S character. So whenever we are talking about the stability of carbanion, we are going to think about three factors. One is inductive, other is a resonance, and third one is percentage of S character. If you have minus R effect, then the carbanion becomes highly stable. But if you have plus I or plus R effect in the molecule, then it makes the carbanion highly unstable. And if percentage of this character is high, then again the carbanion becomes stable. And therefore, alkynes form stable carbanion as compared to alkenes and alkynes. Okay, any doubts? Are you understanding this? What is carbanion and what are the factors which will affect the stability of carbanion? Any doubts?
No, ma'am.
Okay, fine. Thank you. So, Now we have understood what is Carbanion. So obviously we will talk about now what are the reactions where Carbanion is involved. So you'll find that there are many reactions where Carbanion is involved, but most important reactions are aldol condensation, then you have Claisen condensation, then you have Dickmann cyclization, you have Perkin reaction, where generally a Carbanion is formed and they give synthetically important compounds. So let us talk about aldol condensation. So whenever any aldehyde or ketone which possesses alpha hydrogen atom, uh, then they, in presence of base, they form a carbanion, and because they form a carbanion, that molecule becomes that molecule can easily lose its H plus ion to form carbanion. Obviously, carbanion, once it is formed, then it has to react with something else to give final stable product. So it is found that with aldol condensation, you get beta hydroxy aldehyde or beta hydroxy ketone as a stable product. So let us take one example over here. This is your aldehyde. This is a CHO group containing compound, and a carbon to which this functional group is attached is called as alpha carbon. Hydrogen attached to this alpha carbon is alpha hydrogen. When treated with base, hydrogen can be easily removed by this base to form a carbanion. So here we are showing the mechanism that base takes up this hydrogen and this pair of electron can be stabilized over this carbonyl group. If this carbonyl group is not there, this carbanion will not be formed, because what is the factor which is now affecting the stability of carbanion over here? You'll find that it shows a minus R effect like thing and making this particular ion highly stable. So uh, if you see the mechanism now, it is becoming, it is forming a carbanion and it gets stabilized over carbonyl carbon. So this enolate is formed. Okay, once this carbanion is formed, then it can undergo reaction. Why student can't join in time, I don't understand, because every time then I have to keep on admitting them. Okay, so can you see the screen? Yes.
Yes, ma'am.
Okay. So what you'll find that now once the carbanion is formed, then it reacts with another molecule of aldehyde or ketone. Now, yes, if these two molecules are same, then it is called as a self-aldol condensation. And if these two molecules are different, then it is called as a crossed aldol condensation. So in aldol condensation, we have two types. Last time I had shown you the video, and you can always go on YouTube and see the video of aldol condensation, which is uploaded. So kindly go back in and go to my channel and check the aldol condensation again. But here, in short, I'm just telling you that if these two molecules which are going to undergo condensation with each other, if they are same, then it is called self-aldol condensation, and if they are different, then it is called as a cross-aldol condensation. Now what happens? This oxygen gives back its electron, and this alpha carbon forms bond with this carbonyl carbon. So this blue bond is a new bond formed between a alpha carbon of one molecule and the carbonyl carbon of the another molecule. Now whatever you get, now this carbonyl carbon is converted into beta carbon in the resultant intermediate. It undergoes protonation to give you beta hydroxy aldehyde, or if you are taking a ketone, then it forms a beta hydroxy ketone. Now this is the very important product formed after aldol condensation reaction. So only condition for aldol condensation is that out of two molecules which are going to react with each other, at least one must contain alpha hydrogen atom. Now why this condition is there? Because alpha hydrogen can be lost as a H plus ion to give you a stable carbanion. And formation of stable carbanion is the first step in aldol condensation. If I am not getting this stable carbanion, then this reaction will not take place. So it is a two-step reaction. First step is formation of carbanion and second step is condensation. The two molecules, they undergo condensation to give final product as a beta hydroxy carbonyl compound, maybe aldehyde or maybe ketone. So this is your aldol condensation reaction. And as I told you that there can be two types, one is called self, another is called crossed, as if you have two different aldehydes reacting or two different ketones reacting in presence of alkali, then that reaction will be called as crossed aldol condensation reaction. So again, here we are showing that if this is R1 and this is R, that means these two aldehydes are not same, two different aldehydes are reacting, then this is a product of your crossed aldol condensation reaction. So see, many times it happens that you can get two products, one is a cross, another is a self aldol condensation. But maximum you can try to get a cross aldol condensation if you are interested in cross aldol condensation product, and you can avoid a self aldol condensation by just monitoring the amount of these two aldehydes reacting with each other. There is a third type of reaction called as a intramolecular aldol condensation, where same mechanism will be there, that is the formation of carbanion, but only condensation will take place in the same molecule to form a cyclic molecule. So you get cyclic beta hydroxy aldehyde or cyclic beta hydroxy ketone if there is a intramolecular aldol condensation. Now, whenever intramolecular aldol condensation takes place, generally a 5-membered or a 6-membered ring compound as a beta hydroxyaldehyde or beta hydroxy compound ketone is formed. If you are having a smaller ring like 4-membered or 3-membered, then generally intramolecular aldol condensation becomes difficult. So only those compounds which can produce a 5 or a 6-membered ring compound after intramolecular condensation, then only that particular compound can undergo this intramolecular aldol condensation to form a cyclic molecule. So this is about the first reaction, that is aldol condensation, where a carbanion is formed in the first step. So we'll find that aldehydes and ketones only are reacting to form aldol product, because they can form a stable carbanion. So this is one of the reaction where carbanion is formed as a intermediate, and then condensation takes place. So this is your reaction, that is aldol condensation. Then second reaction we had spoken was a Claisen condensation reaction. Now, as we say, condensation means here two molecules are going to get connected with each other. A condensation means generally two things get bonded to each other, get connected to each other. And obviously, if they are neutral, they will not react with each other. So before that, we produce a carbanion from one molecule and condense the carbanion to another molecule. Now, since it's a Claisen ester condensation, you get beta keto ester as a product over here. So just like your aldol condensation, where you get beta hydroxy aldehyde or beta hydroxy ketone, in Claisen ester condensation you get beta keto ester as a product. So generally here bases used are sodium methoxide or sodium ethoxide. So again, Claisen condensation are of two types, self and cross Claisen condensation. Now always remember, when we say self condensation, means two molecules of the same aldehyde or same ketone will react with each other. When we say self Claisen condensation, then two molecules of the same ester will undergo condensation. And when we say crossed, means two molecules are there, but one molecule is from one ester and another molecule is from another type of ester. Then that will be called as cross Claisen condensation. Just like in aldol condensation, two different aldehydes or one aldehyde, one ketone, or two different ketones, when they undergo condensation, we call it as a cross aldol condensation. Similarly, if you have a ester, two different esters condensing with each other, then it is called as cross Claisen condensation reaction. Now, how this reaction takes place? So this is one of the ester molecule. Now you know that ester has COO as a functional group, and it is an electron withdrawing group, which has a minus I and minus R effect. So the carbon atom to which this ester group is attached will always lose its hydrogen, because now after losing hydrogen it can generate a stable carbanion. So you can see here this hydrogen gone, there will be a negative charge on this carbon, but then it undergoes stabilization on this carbonyl to give you a highly stable carbanion. Once the stable carbanion is formed, then second step is a condensation, where now a carbanion or alpha carbon of the carbanion forms bond with carbonyl group of the another ester. So this is a new bond between the alpha carbon of the carbanion and the carbonyl carbon of another molecule. You can see here. Always remember, whether it is aldol, whether it is Claisen, a new bond is formed between alpha carbon of carbanion, and the carbonyl carbon becomes a beta carbon in the product. So now you can see here, this is the product obtained, this is the new bond formed, and you can see now at beta position we have a carbonyl, therefore it is called as beta keto ester is formed as a product. Now you can see here that this is R1CH double bond CO minus OR, and this is R1CH2 COR. So these two these two esters are not same, and therefore this is an example of cross Claisen condensation reaction. And this is how we can show the mechanism for cross Claisen condensation. Are you understanding this? Any doubts? Any doubts? Are you understanding this? Are you there? Are you
Yes,
there?
ma'am.
Okay. Any doubts? No doubts? Shall we go
No,
ahead?
ma'am.
Okay.
Yes, ma'am.
So now we'll go for the third named reaction where the carbanion is involved. That is called Perkin's reaction. Now this is also, see, you can see now whether it was aldol, whether it was Claisen, or whether it is Perkin. All these are catalyzed by base. Why? Because to generate a carbanion you need a base. Okay. So all these are base catalyzed reaction. For aldol condensation, we use 10% NaOH as a base. For Claisen condensation, sodium alkoxide, sodium methoxide are used as a base. Similarly, here in Perkin reaction also you need a base, and here now this reaction is between aldehyde and acid anhydride. They undergo condensation to form the product, that is alpha beta unsaturated carboxylic acid. Last time we had discussed that a cinnamic acid formation is the best example of Perkin's reaction. Cinnamic acid is a alpha beta unsaturated carboxylic acid. If R is equal to hydrogen here, and if this is C6H5, then that will be called as cinnamic acid. This is your alpha carbon, this is your beta carbon. Since there is a double bond located between alpha and beta carbon, we say that this is alpha beta unsaturated carboxylic acid, which is the final product of your Perkin reaction. Now, which are the two reactants which are going to react with each other in Perkin? So you have aldehyde and you have acid anhydride. Now condition is there that your acid anhydride must contain alpha hydrogen atom. Your aldehyde may or may not contain, it does not matter, but your acid anhydride will always contain alpha hydrogen, then only it will undergo Perkin's reaction. Now you know by this time that why you need alpha hydrogen atom. So this alpha hydrogen, once it is lost as a H plus, the base will remove this hydrogen and generate a carbanion at alpha position. So you can see now there is a negative charge on alpha carbon. Is this stable? Then only it will be formed. If it is unstable, it will not be formed. So you'll find that this is electron withdrawing group, COO. Okay, just like ester, this is also a electron withdrawing group. Because the electron withdrawing group is there, this carbanion becomes stable. So a stabilization can be shown over this carbonyl group and it can be stabilized. Fine. Once it is carbanion is formed, then this carbanion in the second step undergo condensation with the carbonyl group of the aldehyde. So you can see this alpha carbanion is getting added to this carbonyl carbon. So all reactions you see, whether it is aldol, whether it is your ester condensation, or whether it is Perkin's reaction, first step is formation of carbanion, and second step is condensation. So all these reactions are condensation. So Perkin's reaction is also a condensation of now anhydride, acid anhydride with the carbonyl of aldehyde. Once this is formed, this is getting converted into OH, and this undergoes dehydration rapidly, and hydrolysis of this ester will give you alpha beta unsaturated carboxylic acid. So this is one of the best method for the preparation of alpha beta unsaturated carboxylic acid like cinnamic acid. Okay. So again, all these reactions are two-step. First step is Carbanion formation. Second step is formation or condensation of Carbanion with the carbonyl group of another molecule. But over here, only one side reaction takes place, and then you get the product, that ester. There are two ester groups here. So one of the ester undergoes hydrolysis and forms a acid group over here. So ester hydrolysis produces acid group in the final product, and dehydration gives you double bond between alpha and beta carbon. So finally you are getting alpha beta unsaturated carboxylic acid as a product in the Perkins reaction. Any doubts? Are you understanding this?
Yes, ma'am.
Okay, fine.
Ma'am,
Any
AC.
question? Yes.
What is full form of ACONA? Base is there.
It's acetate group. Sodium acetate, potassium acetate. AC always stands for acetate, that is CH3CO group. Okay, so
Okay.
if it is acetic acid, it is CH3COOH. If I take acetic acid and treat with some base, you get sodium acetate, which acts again base. So this is a formula for sodium acetate. Okay, so AC is representing CH3CO group. So it is CH3COONA. CH3CO minus Na plus. CH3CO minus acts as a base. Okay,
Yes, ma'am.
you want me to show the reaction for that? How this forms a carbanion?
No, ma'am.
Okay, fine. So here the base is CH3CO minus. Okay, fine. Now next reaction, which is again a Claisen condensation only, but this particular reaction is an intramolecular reaction which was found out by Dickmann and therefore known as a Dickmann cyclization reaction or Dickmann reaction. Now here also you are going to get a beta keto ester as a product, but here you get a cyclic beta keto ester as a product because of intramolecular reaction. Means what? So you can see here, any alkoxide is taken as a base, sodium methoxide, and now you know. Now here you have a molecule where you have two ester groups separated by 3 or 4 carbon atoms. Over here, they are separated by 3 carbon atoms. That means I can generate a carbanion over here at the alpha position, and once the carbanion is formed, then it can undergo condensation within the molecule on over the another ester group. If this happens within the group, then it is going to produce a cyclic molecule. So you can see here, if this carbanion gets condensed with this carbonyl carbon of another ester, then how many membered ring will be formed? So 1, 2, 3, 4, and 5 membered ring will be formed. So you can see here a new bond between now this alpha carbon and the carbonyl carbon of another ester is formed. This blue indicates new bond, and you getting a 5 membered cyclic ring. And then further it undergoes just elimination of OR to give you a cyclic beta keto ester. So since this was found out by Dickmann, we call this reaction as a Dickmann reaction. So this is again another reaction where you are taking a diester, where you have two ester groups are separated by 4 or 5 carbon atoms, and then a 5 membered or a 6 membered ring formation is possible by intramolecular condensation. When condensation takes place within the molecule, then we call it as a intramolecular condensation to form a cyclic beta keto ester as a product. So this is an intramolecular Claisen condensation. It involves base catalyzed condensation of diester to give beta keto ester. Generally, 5, 6, or sometimes 7 membered cyclic beta keto ester are obtained as a product, and you call this reaction as a Dickmann condensation reaction. So, how many condensation reactions we have seen? We have seen aldol condensation, which can have a self and crossed, then intramolecular. So three types are there: self-aldol condensation, cross-aldol condensation, and intramolecular aldol condensation. Self-aldol condensation is the reaction where two molecules of the same aldehyde will react with each other. Crossed is something where two different molecules from different aldehydes will react with each other. Whereas in intramolecular, Within the molecule, you get a carbanion and undergo condensation with the aldehyde or ketone group of the same molecule to give you cyclic beta hydroxyaldehyde or beta hydroxy ketone as a product. So aldol condensation is there. Then we have seen a Claisen condensation. So in that we have seen that it can be self-Claisen or cross-Claisen. But if it is intramolecular Claisen, then it is not called as a Claisen, it is called as a Dickmann reaction. So please remember, Dickmann reaction is nothing but actually intramolecular Claisen condensation type of reaction. The third reaction we have seen, that is a Perkin reaction, which is a good method for the synthesis of alpha beta unsaturated carboxylic acid. So we had seen that in Perkin reaction, aldehyde react with anhydride, which contain at least one alpha hydrogen atom in presence of base to produce a alpha beta unsaturated carboxylic acid as a product. In all these named reactions, carbanion is formed as an intermediate. Therefore, we are studying these reactions, named reactions, in this chapter because everywhere here carbanion is formed. If you see the speciality of starting materials of these compounds, they are either aldehyde, they are ketone, or they are esters, or they are anhydride. Why these molecules are taken? Because these molecules, they contain electron withdrawing group, that is carbonyl or aldehyde or ester, and because of that they produce stable carbanion. And because they can produce stable carbanion, this compound can act as a starting material for these various named reactions. So this is about Dickmann reaction. Any doubts? Any
No, ma'am.
doubts? Okay, good. So another reaction where again carbanion is formed is a Wittig reaction. Very important reaction. Commercially, many synthetic products are obtained by using this Wittig reaction. And for the invention of this particular reaction, Wittig got Nobel Prize. Okay, so very important, and it's a organometallic type reaction. So what is this reaction? So this is one of the reaction by which you can convert an aldehyde or ketone into alkane in one step. So very therefore it has a very much commercial importance, because I can, in one step I can convert my aldehyde or ketone into alkene. So when aldehyde or ketone reacted with Wittig reagent, now this particular reaction was, as I told you, that was found by Wittig. He introduced a new reagent called as a Wittig reagent, or it is also called as phosphonium or it is also called as phosphorane, one and the same. Okay, Wittig reagent is called as phosphorus ylide, phosphonium ylide, or phosphorane, one and the same. And its structure is like this: PPH3 thrice double bond CH R1 R2. R1 R2 can be anything, it can be hydrogen also. So this particular reagent was invented to convert your aldehyde or ketone into alkene by Wittig in one step, and that is why he got, for his great contribution, he got a Nobel Prize. Now, how this reagent is formed? So it is actually two-step again. That first you prepare a Wittig reagent, and then second you will react it with the aldehyde or ketone to form alkene. Okay. Now, what is how the preparation of Wittig reagent takes place? So here you require alkyl halide and triphenyl phosphine. What is triphenyl phosphine? It is PPH3 thrice. Okay. Now you know that phosphorus has a lone pair of electrons, just like you know that nitrogen and phosphorus, they belong to same group. Nitrogen also has a lone pair of electron 1, and phosphorus also has one lone pair of electron. Because of presence of this lone pair of electron, they become good nucleophiles. They can donate their electrons, and they are nucleophilic in nature. So if I take alkyl halide and if I take triphenyl phosphine, they undergo nucleophilic substitution reaction. Now what happens? This is your nucleophile which will donate electron to this alpha carbon, and X will go as a leaving group. If that is so, since phosphorus has donated its electron, phosphorus acquires positive charge. It has formed now 4 bonds. In PPH size it had only 3 bonds. Now it has formed a new bond with this carbon, which is CH2R. So this CH2R is still as it is, but phosphorus acquires positive charge. And this X, since anion remains in vicinity, a salt like Wittig salt is formed. Okay, this salt is formed. Then this salt is reacted with a strong base like lithium compound. Okay, this ionizes to give Ar minus and Li plus. This Ar minus, what it does, it removes one of the hydrogen attached to the alpha carbon atom. So there is CH2 over here. If I remove one hydrogen here as a H plus, this becomes a carbanion, and this carbanion is formed. Now this is negative, this is positive. Very good communication between them, and they form a double bond, and you get this Wittig reagent. So you can represent Wittig reagent in this manner or in this manner, one and the same. This is also a Wittig reagent, this is also a Wittig reagent. So first step is formation of Wittig reagent. And if you see now this reaction, Wittig reagent, a carbanion is formed, and therefore we are studying this particular reaction under this chapter. So first step is formation of Wittig reagent. What is required for formation of Wittig reagent? You need an alkyl halide, you need a triphenyl phosphide, and you need a base. First, alkyl halide and triphenyl phosphide react to give this positively charged intermediate, which can easily lose its alpha hydrogen atom in presence of base to form a reagent called as Wittig reagent. So this Wittig reagent is formed. Once this Wittig reagent is formed, then it is going to react with your carbonyl compound. Now carbonyl compound means it will react with aldehyde or ketone. Now this carbonyl compound and this Wittig reagent, now this is your carbanion, undergo nucleophilic addition to this carbonyl carbon, and this O minus gets attached to this P. So 1, 2, 3 and 4 centered 4-member ring is formed. That is called betaine intermediate. So you can see now this, there is a 4-membered ring formation. This intermediate is called as betaine intermediate, which breaks down to form an alkene. Now you can see a C double bond O is converted to C single bond O in betaine intermediate, and then this bond is broken completely between carbon and oxygen, and a new bond is formed between another carbon. So single bond will be converted into double bond. So you get alkene as a product and triphenyl phosphine oxide as a byproduct. Always remember, this is the byproduct, common byproduct in all Wittig reactions. So a Wittig reagent adding to carbonyl carbon the carbanion, and oxygen getting attached to this phosphorus gives you this betaine intermediate, and this betaine intermediate then undergoes breaking of bonds in such a way that carbon to oxygen bond is completely broken to form an alkene, and triphenyl phosphine oxide is given as a byproduct. So this reaction is called as a Wittig reaction, one of the best method for the synthesis of alkene from carbonyl compounds like aldehydes or ketones. Any doubts? Understanding?
Yes, ma'am.
Okay. Okay.
Yes.
Hopefully, yeah, fine. So this is the your Wittig reaction. Let's see now one more Wittig reaction. So you have a aldehyde over here, okay, and you have your reagent. Now, if I want to find out how I'll prepare this particular reagent, so very simple. This is your carbanion, okay, and this is your triphenyl phosphine. Triphenyl phosphine is common everywhere. Now what you will do here, just add one hydrogen. So it becomes RCH2 and X will be attached to it because we are going to take alkyl halide. When I remove hydrogen by using base, it becomes a carbanion and reacts with your triphenyl phosphine to give you Wittig reagent. Wittig reagent, carbanion adds to carbonyl carbon and oxygen gets attached to this phosphorus to give you betaine intermediate. Now there are two possibilities are there. What two possibilities are there? That I can add, there is a syn addition reaction, that is syn oxophosphate will be formed, a betaine. Syn means what? R1 and R2 to the same side and hydrogen are to the same side. You can see here there are two hydrogen and there are R1 and R2. If they are to the same side, then it is called syn addition, and they will form a Z alkene as a product. Z means what? R1 and R2 to the same side, HH to the same side, and this is the betaine intermediate form. What is another possibility? That you can have a anti-oxophosphate formation where now R1 and R2 are opposite side, two hydrogen are also to the opposite side, and you get this betaine intermediate. So if this happens, you will get E alkene, that is trans alkene as a product, here syn alkene as a product, here hydrogen are across, R1 and R2 are also across, so this is E alkene. So it is observed that whenever these two possibilities are there for the formation of oxaphosphotate, it is observed that anti-oxaphosphotate is more stable as compared to syn. Because anti is more stable, you get E-alkene as a major product, whereas Z-alkene is obtained as a minor product. What is Z-alkene? It is cis. And what is E-alkene? It is trans. So, out of two alkene, even though you are getting these two products, one will be major, other will be minor. So, which will be major? E, that is syn will be trans will be major or anti will be major, and cis or syn will be a minor product. So this is a reaction which is we are calling that it's a stereospecific reaction. Why we call stereospecific? That even though two possibilities are there, you don't get 50% of Z and 50% of E. You get one selective product as a major product, and such kind of reaction is called as stereoselective reaction. So Wittig reaction is a stereoselective reaction. I started with aldehyde. A carbonyl group is converted into C double bond C. So I get alkene as a product from carbonyl in presence of Wittig reagent. So this is called Wittig reaction. Any doubts? Hmm? Are you understanding this?
Ma'am, how we will decide in mechanism that it undergoes E alkene or Z alkene?
See, there are many references or many evidences are given for this particular reaction, but because it is not in our syllabus, only thing you please remember that out of these two intermediate, which is more stable intermediate, so you'll find that if R1 and R2 to the same side, a four-membered ring means both nazdik hai, 90-degree angle hai, or R1 or R2 close aa jaye, so there is what steric repulsion is there. Here in R1 and R2 are opposite, so there is no steric repulsion. Because there is no steric repulsion, this anti will be formed as a major intermediate as compared to syn. And because this is obtained easily, as it is not sterically crowded, you get a alkene as a product and not as a Z alkene. Just try to understand this, that which intermediate is more stable, that product will be a major product. And you'll find that since anti-oxophosphatane is sterically less crowded, it will be formed easily, it will be more stable, it will be major, and that will corresponding alkene will become a major product. And therefore, E alkene is getting as a major product and Z is a minor product. Right? Are you understanding this?
Yes, ma'am.
Okay, any doubts? Hmm?
No, ma'am. No, ma'am.
Okay, right, fine. So this is first part of the chapter that we are talking about Carbanion, then its stability, and then we are talking about its application for the synthesis of various molecules. Now, second section of this particular chapter is synthetic applications of this particular reactions. What is the use of this reaction, aldol, or whether it is Claisen, or whether it is your Perkin, whatever. So they are called as the synthetic applications. So tomorrow we'll talk about the synthetic applications of these uh, reactions. Today we'll just talk. We have spoken a lot about many reactions, many mechanism, and many factors. How the stability of carbanion is decided. So I think that much is enough. Already, since we had done this in the previous classes, that is why rapidly we have gone through. But try to remember and revise these things, because otherwise it will be very difficult for you to cope up with the syllabus. Okay, so we'll stop here, and tomorrow we will talk about